we're going to welcome SEA and Jacob Bro. He's going to give a good presentation this morning. Thank you.
Good morning. Thanks, Adrian. I'm happy to be here. Again, my name is Jacob Bro. I'm with Swagelok Energy Advisors, and I'm going to be talking a little bit this morning about steam leaks and maybe even start off the conversation just with leaks in general. Within that first minute and a half introduction, you probably realized that I'm not from Tampa. I am from New Orleans. At the end of the presentation, I'll open it up for questions, but I'm going to go ahead and answer two of them right now. I do not know, nor am I related to anyone on Swamp People, and I know no one from Duck Dynasty. Matter of fact, where I'm from, where they filmed Duck Dynasty is Arkansas. So if you're above I-10, where I'm from, you pretty much live in Arkansas. But anyway, no, I'm from New Orleans, South Louisiana. Closest point of reference is New Orleans, and I am happy to be here to present and talk a little bit about leaks. This presentation is predominantly about steam leaks. Talk a little bit about compressed air leaks too, just to try and quantify them and understand, the losses, whether it be energy losses, whether it be loss of reliability, safety issues, whatever the case may be. Let me say this, I'm a mechanical engineering graduate, and I actually started my career in the oil field. And on a lot of these platforms, as well as a lot of plants, I'm sure most of you are familiar with fusible loops. These are installed so that in case of a fire, there's a fusible plug, it burns out, it releases the air, there's an emergency shutdown. About 6.5 months into one of the largest oil and gas producing platforms at the time, we had leaks so bad in some of our fusible systems that it simulated a burnout, and it would cause the entire platform to shut down. So I was under a lot of pressure. So my point being is that leaks have been near and dear to my heart for a long time. They came up to me, I was the lead facility engineer for the platform, and said, hey, we got to get this resolved. At that time, oil wasn't $90 a barrel, but it was still pretty profitable, and we were doing about 80,000 barrels a day and about 300 standard cubic feet of gas a day. So when that platform shut in, it got a lot of people's attention. So my point being is that leaks, whether it be steam, compressed air, on any facility, I've tried my best to think of applications that leaks are a good thing, and I can't come up with one. Maybe, possibly, when you're commissioning and hydro testing or starting up a system, a leak will tell you, hey, you need to retighten something or fix it. That's about the only application I can think of that it would be good. And that's what I'm going to try and focus on today. I'll show you a couple of calculations to quantify them, but the basic part of the presentation is that I really can't see any good applications for them, and any effort or every effort should be made to correct them. They have a negative effect on the steam plant, whether it be energy losses, which is pretty obvious, right? Steam is not free. You have to do something in order to create it. If you lose it, you're losing money. Increased emissions, you're having to use the boilers more, possibly even run another boiler. Loss of reliability, production issues. So leaks are a form of flow, pressure drop. You're losing pressure, you're losing temperature. So if you have tracing systems and you're losing temperature, that may be causing you production problems. And then obviously it's a safety. Not only because it's hot and it can burn you, that's pretty obvious, right? But during the wintertime, it'll cause freezing problems. The losses can be as high as 19%. So let's just say, for instance, you've got $1 million fuel budget, that's $190,000 potentially. And every plant's different, and I want to make that clear from the start. I'm not giving you a fact of any plant. I'm giving you rough ideas of what we've seen throughout our work. You could be losing $190,000 just through leaks of various sorts. Leak correction has the biggest payback. We get asked a lot of times to come into plants to do audits for various reasons, whether it be production issues, whether it be energy issues, water hammer issues, you name it. And we're always looking at potential payback and return on investment. So a lot of times we're looking at, obvious things like insulation, possibly a high pressure condensate return system, improve that thermal efficiency. But without a doubt, leak correction has one of the greatest paybacks. A lot of time is spent, and to good measure, replacing steam traps, testing them. But if a steam trap fails and you have the proper condensate return system, you're losing the latent energy. You're not losing the total energy if you're recovering it. So again, although it may not get the attention that a lot of the other aspects of steam systems and the reasons we get brought into plants to do work, leaks themselves can save a whole lot of money. And just as much, if not more, than some of these things. You know, we'll spend a lot of time on boiler operations and whatnot. But I'll tell you, you go out there and you're working on things, a high-pressure deaerator, whatever the case may be, and there's leaks everywhere, and you just wonder to question yourself, hey, you know, this is the obvious. Fix them. You know, we get into this because we do both. We work with both. We work with steam. We work with compressed air. Kelly Paffel, who's the technical manager for SEA and my mentor and who I work with quite a bit. Today he's actually beginning an audit, and I just learned from Adrian it was a compressed air. I thought it was steam. Nevertheless, you know, a lot of interest gets paid to both of these. Now, I'll say this. Again, I'm from South Louisiana. I live in the heart of sugarcane country. There are 8 major sugarcane mills where I live. Their byproduct from sugarcane is bagasse. Their boilers burn bagasse. It's essentially free. So if someone from a sugar mill is sitting here today, they're going to argue this point, and they're going to say, no, we're not paying $10 per 1,000 pounds. Our compressed air is actually costing more. Great, fine, whatever. It's still costing you money. It's a leak. But in this case, the case we're making here is that oftentimes we do spend a lot of time on compressed air, not realizing that the cost for steam, and I would say right now, in today's market, natural gas prices, $10 per 1,000 pounds is probably a little high. It would definitely take into account a loaded costs. You know, that would be fuel costs, boiler efficiencies, and then all the water and chemicals and whatnot. But for the sake of discussion, we'll go with $10 per 1,000 pounds, 100 PSI. You know, you're looking at about a $1,500 difference over the course of a year at the same pressure with the same leak. And truthfully, in our business, most of our work is with steam. We do compressed air, but most of the work is with steam. So the question becomes, okay, we know it's not wanted. We know leak is an undesired flow path. How much are we losing? How much is going through this leak? Well, you know, is the size, here's the leak. So it's 1/8 of an inch, 3/16, 1/4 of an inch, whatever the case may be. And it's the steam pressure. And then the downstream pressure is always atmospheric. Obviously, it's leaking, it's going to atmosphere. So a leak calculation is no different than any other fluid flow calculation. It's due to pressure drop and orifice. The only constant in this case is that it's always atmospheric pressure. So here's the basics. P1, P2. 50 pounds to 0, 150 pounds to 0. Which one's going to have the higher leak rate? 150 to 0 or 50 to 0? 150 to 0. So a lot of these things that I'm telling you are pretty elementary, but I'm going to tell you, so you fix the high pressure leaks first. That's where you're losing the most steam. That's where you're losing the most energy. However, if it was that easy, it'd be done probably more often. But a leak is not perfect. A leak is leaking around the threads of a connection. A leak is coming through the packing of a valve. A leak is at a flange point. It is not a perfect circle that you can run a perfect calculation on. So in order to try and understand it and better quantify the leak, there's been a couple of constants developed. The reason that is because, as I was just describing and giving you examples of potential leak points or potential leak applications, it's going to be jagged. It's going to be a crack in a line. It's not going to be a perfectly symmetrical orifice. Now, a lot of times we get into discussion about plumes and how long the plume is, and it'll tell you the length. Well, here's what I'd like to say. Test results indicate not a significant difference between the plume when varying the orifice. However, pressure varying has a significant difference. So here, you know, you've got a smaller leak. This is just a representation of the orifice of potential total volume. 50 pounds to 1 to 0, the example I just gave you, may be 6 inches. And when I say 6 inches, I'm talking about to the end of where you can see any kind of velocity, and then the wind just starts kind of wisping it away. Well, you can have 150 pounds, but if you've got a larger orifice, and believe me, it's not that easy to look at it because it looks like fall. I mean, a lot of times you feel like you're at a rock concert and you're the start opening band because you're coming through this smoke screen when you're trying to look at this stuff. But the fact of it is, you don't know. So if the plume's 6 inches, so if you're looking at this, let's say you can see some velocity coming out. And by the way, In order to have velocity, you have to have pressure. So that's what's going to be driving this. But it's 6 inches, and this one looks to be a 6 inch, and these are rough estimates. Well, you have no idea if it's the same volume just by looking at the plume. It's highly dependent on pressure. That's what I was just saying. The volume, however, is dependent upon the orifice. The actual loss is going to be dependent upon how big it is. I mean, that only makes sense, right? So if we look at this, at 250 pounds and through an 1/8 inch leak, you know, this goes through, now this carries through our $10 per 1,000 pounds that we established earlier, right? Almost $8,300 a year on a 250 pound leak at 1/8 of an inch leak, and that's estimated. However, you go up 3 times in the leak, you go up nearly 9 times in the cost. And we'll see soon why that is, and you probably know why that is, because in any flow calculation, the diameter is squared. So when you start looking at leaks and you start increasing that diameter, it being a squared function, your cost per year and your actual volume is going to go up 3 times, as in the case here. Again, just going back and looking through it, and it stays the same, you know, for most of these. So you're going from, you know, same pressure, but, you know, 9 times the cost because of that leak. So what is the equation? It's a variant of Napier's equation. There are different variations, and this 22.8 is simply a constant that's been derived, that's been accepted, that we use, and I think I've seen this number 23 or 23.5. The fact of the matter is, this is simply an estimate. It's a best guess. It's through testing, that's what we've come up with. This is the point that I was making here, though, is the diameter squared. Fix the big ones. That's the ones that's costing you. I mean, it's, you know, it's pretty obvious. It's right there. It's math. It's not magic. So, looking at a couple of examples. Here we've got a distance, you know, and this is what I'm talking about when I say the plume length here, is this 6 inches. You got a 3/4 inch valve, maybe a third of the way opening, so we're estimating now, you know, a 1/4 inch leak at a pressure of about 140 psi. Really, what I want you to see in this picture is the valve's not leaking, the valve's open. Why is the valve open? More than likely, you know, they're having problems here at the steam trap, and so they're not getting condensate through, so they're opening this out to drain the condensate so they can maintain temperature. A lot of leaks. I see one guy shaking his head, and I've hit with someone. How often? I tell you what I need to be in. I need to start selling hoses, because most of the time there's a hose from here to the nearest drain. That's the reality, you know. So when I that's another subject. That's part of our STEAM classes. But, you know, just to kind of talk about it a little, you know, what I hope you get from this is when you walk by this, put a number to it, $15,000. $15,000. So not only are you losing energy, you're creating a safety hazard, you're having to produce more steam. Everything I said at the beginning of the presentation holds true in this just one little simple application. Any questions or comments, or I don't want this to be a death by PowerPoint. Please stop me at any point and ask a question. I don't mind at all. And if I get off a little bit on you know, other subjects of STEAM, just kind of get me in line, but I just like to tell you a little bit as I go, because I see it all the time. Again here, now, you know, here we go, and I know this is kind of, I should have put some on the same screen, but, you know, 1/4 inch leak, 3/16. So now we've dropped down a little bit. We've actually increased the pressure, but again, because of that diameter, going back to that diameter being a little bit smaller, you know, again, just understanding costs. This, you've got 250 pounds, same leakage, same leak estimate. Okay, now this is obviously, these are all estimates, and that's what I'm getting back to. You know, your cost is going to go up. Higher pressure, same diameter, you go up 100 pounds, you know, you're increasing your cost by almost $8,000 a year from a leak standpoint. Now, here's a question for you. So we've got the equations, we understand the equations, we can do it. We walk by and we see this. Now, anyone want to take a guess what that leak rate is? You have no idea. It's on the ground. You know, there's no way you can quantify this. What do you think the plume length is here? Any idea? Hose is here. And I want to go back to this one and just stop it here for a second. And I'm going to touch on a lot of these things throughout the presentation. But, you know, one of the things that we're big on, especially when it comes to condensate systems, off of drift pockets, off of small loads. You know, you can't do this off of process heat exchangers, but, you know, we typically tend to stay and use more tubing, tube fittings, stainless steel. And why is that? Because when people are designing condensate systems, they'll use Schedule 80 piping. You know why? It buys them a little bit more time before the carbonic acid eats through it. It's not for pressure. It's for a little bit more longevity in that piping system. And then what do? Then they thread it. And guess what happens when you start up and shut down steam systems and condensate systems? They expand and contract. And where is the expansion and contraction going to take place? At the threads, which is now the weakest point. So you've bought a big old thick pipe, but then you've threaded it, and then you've made it where you've left no room for expansion in a system that is going to start up, shut down, and expand and contract. Guess where your leaks are going to be? At the threads. That is and these are just more and more videos, but I want to get to some of the presentation here. So, connections, I just talked about that. Expansion and contraction, erosion, valves. You know, this is classic. This is classic. So, people buy valves that leak. Did you know that? How many buy valves that leak? Come on. You know, here's the deal. When you woke up this morning, you went and you brushed your teeth, you were operating a higher shutoff class valve than most people buy for steam systems. If you're buying less than a class 4 shutoff, it's going to leak. You install it, it leaks. So then what happens? Then you get somebody out there with a 36-inch pipe wrench and a 4-foot piece of conduit, known as a cheater, and you get on it and you mash it, metal to metal. And I'm going to tell you, the best you can hope for is that it starts leaking. The worst thing that can happen is you break the bonnet and you got a nanosecond to get out of there. It's done all the time. There's higher quality valves in hotel bathrooms than there are in steam systems. But yet, we wonder why we sit through presentations about leakage. I mean, it's, you know, it's right there in front of you. There are quality valves. Do they cost more? Absolutely, no doubt, up front. Longer term, if you believe some of these numbers and you look at these leak rates and you look at the potential savings, I would argue it's a better, it's a better payoff. Steam traps. Now, I have to be careful. There may be steam trap people in here, but I would say no matter who steam trap, no matter what design steam trap, floating thermostatic, mechanical, thermodynamic, they leak. Why? Because one of the functions of steam traps is venting air. Very, very poorly, I might add, but they vent air at startup. Well, in order for them to vent air, they have to lose a little bit of steam. That's a fact. Expansion and contraction from steam, carbonic acid. So why is this a big deal? Everyone runs steam systems. I say everyone. I don't know of a case, I haven't seen one, but you've got deaerators. They do a pretty good job of venting non-condensables, but it's not perfect. Things condense, CO2 forms carbonic acid. It will eat away at carbon steel. Again, going back to the condensate systems and why, you know, we're a proponent, and I think most of the, you know, there's some inherent benefits to using stainless steel over carbon steel for condensate systems. And then leaks will be created by there. Here's the deal. A small leak today, a bigger leak tomorrow. The valve I just told you about. So now you mashed it. It's closed. You did your job. Now you got to open it. And a lot of times people open valves without warm-up valves. So they're taking a valve that big and trying to just barely open it. Well, guess what? when it barely opens and you create that pressure drop, it'll cut it like that. It'll wire draw over time, and your small leak, your 1/8 of an inch becomes 3/16, becomes quarter, and now it's really costing you a lot of money. Let's talk a little bit about emissions. So if you're losing this steam and you need this steam, you're having to make up for it. We all know about emissions. We all know about the emphasis on it right now. This is fossil fuel emissions, pounds per billion BTU of energy input. So, as I said earlier, there are multiple fuels being used for steam production within boilers. I've just put a couple of them up here. But these are the type of numbers that, hey, you got 2 boilers and you're running both of them at, let's say one at 60, one at 40, whatever it is to maintain it. Is there potential to turn one off? And man, nobody likes that. Well, why you got 2 boilers running? One can do it. Well, just in case. Just in case. Okay, so you're running it less than 40% firing rate, which the excess air is great. The efficiencies are horrible. You're costing yourselves emissions, and you're producing steam that you really don't need, but don't worry about it because you're leaking, so you're losing it. So when I fly back to New Orleans tonight, how many cars do I have in the parking lot? 1. I don't have another car just in case. I mean, really. So, the point is, do the maintenance, do the PMs, you have a boiler management system, try, look at ways to reduce leaks, and just, I guess my point is, and I learned this from Kelly, his favorite word is don't componentize. People love to componentize systems. Oh, it's a steam trap. Well, no, it's not a steam trap. You're trying to elevate condensate 30 feet, and you're losing differential across the trap. It's backing up condensate into the heat exchanger, and that's what's causing the water hammer. Anyone ever tell you that their trap handles water hammer better than anyone else's? Just see them out, wish them a good day, and that's a ridiculous statement. Water hammer kills people. It's not the trap's problem, it's a piping problem. The picture I showed you with the leak, it's probably not the trap's fault, it's probably a piping problem. Then this is my favorite. They come out the steam trap. As soon as they come out the steam trap, they reduce the piping size. Why would you do that? Condensate is 2-phase. They size condensate lines based on liquids. Condensate is a 2-phase flow. So as soon as that condensate comes out of there, sees a pressure differential, a percentage of it is going to change state and re-vaporize. It's going to expand, but yet people reduce the pipe. These are just tidbits of things that you need to be aware of and look at and think about, why are we doing this? Okay, back to leaks. Valve selections, I've already kind of touched on this. Isolation valves are purchased already have internal leak rate. Someone can tell you, my valve doesn't have to meet a leak rate. They are 100% absolutely correct. If it's a class 1 valve, you don't have to meet it. It's up to us as consumers and engineers and project managers to specify a valve with a leak rate. This is not a good picture, but this is a valve here that's actually leaking through the packing. Again, all my points here is that leaks don't come in a nice little package. They come in a variety of forms. They come from threads, they come from valve, they come from packing. Why am I showing you this picture? I don't know why I don't want to. I apologize. I wanted it to stop on that picture. A lot of times we'll start talking about steam quality. People ask us about steam quality. And there's a lot of different ways you can test steam quality, laboratory type tests to get official. But a good rule of thumb is, open a valve, and steam is invisible. Steam is not that white puffy cloud that you see. Steam is an invisible gas. So when you open a valve, if you've got good steam quality, there should be about 2 inches that you see nothing. It's absolutely invisible. So my question to you, what do you think of that steam quality? Poor. Very poor. But the reason I bring this picture up is because during an audit, during a needs assessment within a facility, we'll be walking around and we've been told, hey, we've got poor steam quality, yada yada. So we'll ask someone, can we open a valve? Well, that requires a work order, it takes a while, but the point of the story is they don't want to do it. And we're like, well, we want to just get a look at it. Why? because they're afraid once they open it, when they close it, it's still going to look the same exact way. Just what you see. I mean, this is real life. This is what happened. They're hesitant to open a valve, not knowing that when they close it, it's going to shut off. This is what I was talking about earlier when I talk about, so if you remember back to my opening slide, I talked about energy losses, I talked about emissions, I talked about production issues, I talked about safety issues. And one of the things here with production, it'll lower pressures. Steam tables. For a given pressure, there's a given temperature. 100 psi steam is 339 degrees. 99 psi steam is something less than 339 degrees. So if you have a system that is designed for a given temperature, i.e. pressure, and you no longer have that pressure because you can't maintain it because you're losing it due to leaks, then you no longer have the temperature that system was designed to. So when I talk about production issues, that's what I'm talking about. That's the production issues I'm talking about, is that a drop in temperature, a drop in pressure is a drop in temperature. If a process needed a certain temperature, you no longer have that. And then safety. These are pretty obvious. Personal injury, burns. Unfortunately, I will say this, I haven't been involved in a incident investigation. Some of our other engineers have, but I have been involved in training for folks who had an incident, and part of the follow-up was they needed training, so we did the training, and I'll tell you, it's not very fun, and it is very, very real. So burns are obvious. Fog conditions. If you think back to that video I showed you with the two big steam traps and there was just a fog everywhere, I mean, that's dangerous. I've been in situations to where I couldn't see someone from me to the table because of the fog that's coming up. Those are dangerous situations. And this is the deal. And Kelly said this first, and it's so true. If I go into a plant and I have to get on a ladder higher than 6 feet, I need harness, I need to go through training, I need to do all these things, but yet I can walk by and they got 100 psi steam leaking, blowing out the pipe. And for me, it's hard to fathom. I'll tell you what, I'd rather take my chances on a ladder than walking by a bunch of 100 psi steam blowing out. I mean, it's up to you, it's your choice, but I know what I would rather do. I'm much more comfortable on a ladder. Obviously, steam condenses, forms condensate, and then maybe not in Tampa, maybe not in South Louisiana too much, but in the colder climates, it'll freeze, and that becomes a hazard. So, what can we do? What is the message here about leaks? Leaks to me is just an unwanted flow path. That's what I describe them. If anyone has an example of a good leak, please let me know, and I'll use it the next time I do this. But I can't really think of any application that they're a good thing. Buy the right valves. Buy the right valves with the right packing, valves that don't leak internally. That's a good starting point. Condensate systems, stainless steel, for no other reason than you're going to have carbonic acid. The best deaerators, the best chemicals in the world, you're still going to have some carbonic acid. Here you can use universal connectors, eliminate the threads. This is available on our website, Swagelok Energy Advisors. We've got 33 best practices. They're free. There's no charge to them. They talk about best practices and they talk about standard connections. And I'll just give you an example here. So if you were to look at this, here's a drip pocket coming off of a pipe. Very well designed. 8-inch pipe, 8-inch drip pocket. I love to see these 12-inch pipes with a 1-inch drip pocket. I'm not sure what they think they're accomplishing, but it's kind of like when I'm putting and the ball goes right over the hole. You're not accomplishing anything. We have best practices on that, as far as diameter versus drip pocket. This is not, and don't get me wrong, this is not at any means a bad design. This is done properly, but at each arrow, there's a connection. There's a threaded connection. One thing while I'm on this, I'll make a note. When you see this here, this is actually done correctly the way we would recommend doing it. Don't put the blowdown valve right here, because all your trash is going to fall here. And then, or I should say trash, I've been corrected. Your corrosion products are going to accumulate here. And when you open the valve, it's going to come through and it's going to cut the seat, and that, my friend, is going to be one of those valves that don't close. So come up a little bit, maybe, as they say here, 3 inches, maybe 6 inches, and that way, you know, you're not getting this corrosion product here out the valve. So again, just a little tidbit of information. But what I want you to do is I want you to compare that to, you know, using a tubing system for this. There's 1, 2, 3, 4 connections, and inherently, it's stainless steel. Or if you do use carbon steel, you still get some of the benefits, but if you use stainless steel, you can fight the corrosion. But if you'll see here, these bends will inherently take up the expansion and contraction. And that's to me as much important as the stainless steel. So everything else is done the same. If you were to look at this from a P&ID standpoint, as far as isolation, drain traps, drain valves, it's the same. You know, the point is, we can no longer accept steam losses to atmosphere. There's really no reason. There's a lot of things you can do. Pressurized condensate systems, you can use thermal compressors. If not, you can use vent condensers, heat up water, do something. You know, when you drive by and you see this, that's a problem. I mean, we all know it's a problem, right? And it's what I talked about maybe a while ago. It's people not understanding that, you know, they have a condensate tank that, because it's being pressurized, because steam traps are blowing into the condensate system, the pressure in the condensate pot is rising, the pump is losing suction head, it starts to cavitate, so now you start backing up condensate into the heat exchangers, then you're generating water hammer. I can promise you this, you know how I know the pressure is increasing in the condensate tank? Because of the velocity. You're not going to have this type of plume if you don't have velocity coming out of the condensate tank. So we can't accept it. This is what it should look like. This is what it can look like. Swagelok Energy Advisors. Again, what we are is a STEAM training, consulting, engineering arm, I guess you will, of Swagelok. I know many of you probably know of our parent company. They've been around for 60 plus years selling tube fittings and valves and whatnot. But we're simply an engineering part of that company doing strictly compressed air and steam. We've got training programs. As we mentioned earlier, we work in conjunction with UE, actually hands-on training with the ultrasound for our steam trap examiner course. And these are some of the programs we offer. And again, this is just a real quick little ending up to my talk here, but I will stick around for lunch. I'd be happy to talk to any of you about specifics on any of this. Audits, you know, implementation recommendations, engineering, design, equipment, and in return on investment. You know, we can go in for a day, we can go in for 2 weeks. So this is what I really want. Why do audits, you know, why do audits on your own, not just us? Over 25% of the steam generated is wasted. Again, these are just industry numbers. These are not our numbers. 20% of steam applications can be satisfied with lower pressure. What has more usable energy, 4 psi steam or 100 psi steam? Usable energy, 4. 4 psi steam has more usable energy. You ask customers, what's your boiler? This is the first question. What's your boiler output? 250 psi. Why? That's what it is. You know? Now, please don't go run and reduce your boiler pressures because they're designed for a certain thing. But my point is, if we would have stepped through the calculation for the cost of steam, so I gave you that number. I said it was $10 per 1,000 pounds. If we actually step through the equation, you will see a direct correlation between steam pressure and steam costs. The higher the pressure, the higher the cost. All things being equal, higher pressure steam. So just simply do an evaluation. Now, we've done some work with particle boards and board manufacturers. There are glues in there that require a specific temperature to make it set up. Well, fine. Then you need 230 psi steam because you need the temperature. So it's a matter of what do you need the high pressure for. If you need an exact temperature, fine. But if not, just reconsider and say, hey, are there ways that I can lower my steam pressure and essentially reduce my costs? Boiler efficiencies, you know, are new steam traps required? These are the kind of things we talk about because here, you If the thermal cycle is only 43% efficient, we can go out and we can change traps, we can put insulation, we can do a lot of different things. It's not going to have that much effect on it. And then understanding performances. Everything we do per the codes, B31.1 if we're over 15 PSI. And that's really all I had to talk about this morning.
Good job.